So, this expression once again is of the form A cross B cross C, and we know that this is an identity, and if we write this, it will be, so A cross B cross C is equal to B times A dot C minus B times A dot C minus A times, I think, right, sorry, C times A dot B, C times A dot B. So, that is an identity we all remember. So, using that identity we can put this, and using this identity we can write L is equal to sum over I m I. So, it will be omega times R I square minus C is equivalent to R I times R I dot omega, right. So, this will be the expression. Now, if we open this, so these are all vectors. So, there is a vector dot product, and this is a vector here, it is a vector here. So, if we open it up, what we will find is sum over I m I. So, the first term will be omega x. If we take omega x common, it will be R I square minus x square, sorry, R I square minus x square, this will be one term. Then there will be additional term of minus y x minus z x, right, right, and there will be additional term of y. There will be two more term of omega y, just give me a second. So, it will be R x square, right. So, we will have terms like minus y x plus R I square minus y I square minus y z plus omega z minus z x, no, it will be x square, right, minus z y plus R I square minus z square, right. So, omega x, omega y, omega z, and we have an m I common here, right. Now, this form can be written in terms of a vector equation. So, we have an equation in L. So, we can write I x x, I x y, I x z, I x y, I y y, I y z, and I x z, I x, sorry, I y z, right, I z z z and omega x, omega y, omega z. Right. So, this particular equation, vector equation, if I break it into components, it reduces to this, and we can write an vector equation or a matrix equation of this particular form, where I x x is equal to sum over I m I r I square minus x square, I y y is similarly r I square minus y square, and of course we have terms like I x y, which is equal to sum over I m I x y, I y z is equal to minus sum over I m I y z, terms like that. So, just for completeness I can write y square, and I z z will be similarly sum over I m I r I square minus z square. Okay. So, I think this forms, probably some of these are familiar to you. If not, let me tell you, these are called moments of inertia, and terms like this, which will be, there will be many more terms, I x y. So, it will be, ideally speaking, it is y x and it is x z, and this is z x, sorry. So, this is z x, this is z y, and this is z z. Right. So, technically we should write not x y, but y x here and x y here. Okay. So, these terms, we see the diagonal term has a specific form, that this is sum over I m I r I square minus x square, r I square minus y square, and z square. Whereas, off diagonal terms also has a specific form, it comes with a negative sign and has a form m I times x y. Right. So, this diagonal terms are called the moments of inertia, whereas the off diagonal terms, they are called the products of inertia. So, these three terms, they are called moments of inertia, and rest, the off diagonal term, this two, this three here and these three here, they are called products of inertia, right. And this whole thing, the matrix as a whole, is called a moment of inertia, in short form MOI, moments of inertia tensor. This whole thing. Okay. So, I think tensor might be a familiar word to you. Some of you might be familiar with this term, some of you might not have heard this term before. Does not matter. We will have a very brief description of what is a tensor. Very brief, because the framework of this course does not allow a detailed discussion on tensor, which will be discussed in your mathematical methods courses. Okay. Also, see that this can be written in an integral form. For example, this one, we can write this as r square minus x square dm, and like before, we can replace dm by rho dv. So, I x x can be written like this. Similarly, a product of inertia, let us say I z y, can be written as minus z times y rho dv, and the integration is always over the entire volume V of this rigid body. Okay. So, we will take up examples on how to compute moments of inertia and product of inertia, but firstly, most importantly, what does the word tensor means? What does it mean, and what do we know, what do we learn from it physically? Okay. So, tensor, first of all, it is a mathematical jargon for any measurable quantity. Vector is also a tensor. Vector is a tensor of rank 1. A rank 1 tensor in a nth dimensional space. Okay. So, let us forget about it now. Let us talk about tensor for a while, then we will come back to the specific cases of moments of inertia tensor. Okay. Let us say if in terms of mathematics, if we are working on a n dimensional space, then a vector which is a tensor of rank 1 has a dimension of n, and this the tensor what we should call it, a tensor of, this is actually a tensor of rank 2 should have a dimension of n square. Now, as the world of rigid body is 3 dimensional, that means according to this law, it will have a tensor which represents some property of a rigid body will have a dimension of n square, which is equal to 3 square equal to 9, which is exactly the case here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 elements in that matrix, and tensor in the tensor of rank 2 is represented by a matrix. Tensor of rank 1, which are vector, they are represented by row vector or column vector. That means, a matrix of this form is a vector which is a tensor of rank 1. A matrix, a square matrix in the world we in the understanding we have, for example, in the domain of understanding, a square matrix is a representative of a tensor. Please understand that all square matrix might or might not be tensor. A tensor is represented as a square matrix, not the other way around. That square matrix is not always a tensor. Okay. So, in this case, a moment of inertia tensor is represented by a square matrix. Similarly, the angular velocity of a rigid body represented by a column vector, right. Similarly, if we have, for example, if we want to determine, if we want to represent a position vector, we can represent it as x, y, z. Similarly, we can represent the angular momentum in terms of omega x, omega y, and omega z, right. So, this is our R. Okay. Now, what does a tensor physically mean? A tensor, if we take the examples of tensors which is associated with some measurable physical property, that essentially means that, okay, if we consider a tensorial representation of a physically measurable property, that means within that representation all the information contained is stored. What I mean is, let us take an example of a block. Let us say this is a metal block for a moment. Let us assume that it is a metal block. Now, we can define the axis as, this is the x axis, this is my y axis, or this is my y axis, and this is my z axis. Okay. Now, if I apply a certain amount of current along the x direction of this box, so I am flowing a current in this direction, and if I measure the voltage across this along this direction, we will get a voltage. Similarly, for this same current, if I measure a voltage between these two surfaces or these two surfaces, I will also get some measurable value, right. Now, if I now represent this, if I now put the current, let us say in this direction, say the z direction, and I measured the voltage in x direction and y direction also in z direction, we will get some number. So, what we can do is we can represent this measurements by this equation. If we know that V is equal to IR, that is our Ohm's law, I being the current, V being the voltage, and R being the resistance. Now, what we can do is we can have a vectorial equivalent of this equation in this particular form, where the current in each of this direction x, y and z will be represented by Ix, Iy, Iz, and voltages which are measured along each of this direction will be represented by Vx, Vy, Vz. Now, because if we have a current in x direction and we can still measure a voltage in y, or actually we can think of it this way, we apply a voltage in x direction, we can still measure, will be able to measure a current along y direction. So, if we, that means we will have a resistance not only along x direction, but also along y direction and z direction. So, we can represent this equation as Vx, sorry, just have to straighten it a bit, Vx, Vy, Vz, which is given by Rxx, Rxy, Rxz, Ryx, Ryy, Ryz, Rzx, Rzy, Rzz, and we will have Ix, Iy, Iz. Why I have taken the example of current and voltage? Because that is something which we will understand more intuitively. Okay, that is something we all, most of us are familiar with, right. So, this Rxs represents the resistance when we apply a voltage along x direction and measure the current along x direction. That gives you some resistance value, and that is represented by Rxx. Similarly, Rxz represents the case when you are applying a current, let us say along x direction, and measure a voltage along z direction. That particular resistance, corresponding resistance, will be represented by Rxz. Now, what is the advantage of such a representation? The advantage is, now once we have this full set of information, that means if we know all these 9 parameters, we know the resistance behavior of this particular, assume that it is a metal block. So, we will know all the informations we need in order to know the resistance of, or information related to the resistance of this piece of metal, right. Then you can put any arbitrary value of Vx, Vy and Vz. That means you can give me any arbitrary direction of voltage which will be applied across it, then I can give you what will be the direction of current, or vice versa. You can apply a current which will be in any direction through this medium. If we know the particular direction with respect to this axis system, I can immediately tell you what voltage will you measure along which direction. So, that means this 3-dimensional representation or this matrix representation of resistance essentially contains all the information you need to know. Similarly, coming back to this, the angular momentum is represented by a tensor equation, or basically a matrix equation. We have a matrix which is a moment of inertia matrix or moment of inertia tensor, and we have this angular momentum. Now, this tells us, if I know this moment of inertia tensor, this can tell me what will be the angular momentum for any given orientation of the omega vector. Okay. So, we have an object. We have an arbitrary object. We have, of course, the fixed point has to be fixed. So, let us say we have, we have some axis system associated with it, and we have a direction of rotation. Okay. So, this direction of rotation will correspond, I mean this angular velocity, it can be decomposed into some axis system which is associated with or associated with the rigid body, or so called the body set of axis. So, omega will have components in the body set of axis, or you can think of it as if, so right now we are talking about an axis system which is fixed to this. We can also think of an axis system which is fixed in space. Okay. So, let us assume that, okay, for now let us assume that we have x prime, y prime and z prime, which is also a valid description, because if you recall, we started with an equation L which was given as I m I r cross omega cross r I, right. So, that was the starting point where from which we got to this equation. Now, if you recall, omega, so r I does not matter if we represent it in body set of axis or space set of axis, because the origin O is the same, and omega is a velocity which is measured with respect to space set of axis. Okay. So, actually L in this equation is represented with this set of axis only. Now, okay. So, for any arbitrary rotation omega, we can always decompose omega x, omega y and omega z in terms of the body set of space set of axis system, and if we know this tensor, I can exactly tell you what will be the value of L, or what will be the direction of L vector for this value of omega. You change omega to, or you change your axis here, and you have another value of omega which is omega prime, let us say. Don't, okay, so we will just call it omega 1 and omega 2, okay, just to avoid any confusion. And now also if I can decompose omega 2 into x y and x prime, y prime and z prime system, and I can immediately give you the knowing the moment of inertia tensor, I can immediately tell you what will be the value of nu L, right. So, this is the advantage of having the tensor. Of course, getting the entire tensorial information, that means knowing all 9 components of the moment of inertia is a tedious process. We might need it, we might not need it at some point, depending on the geometry of the problem, depending on the symmetry of the problem. We have to decide whether we have to go for we have to go for calculating all 9 components, or we can just use a reduced set. But what is important is all this moment of inertia tensor, which essentially contains all the information you need to know about the rotation about this fixed point, might will not be valid if I now move the shift point here, the fixed point here. So, moment we shift from this fixed point to another set of fixed point, we have to recalculate the entire moment of inertia tensor. So, moment of inertia tensor of an object is defined with respect to a fixed origin. It is not a general description. Please keep this in mind. Okay. But okay, so ideally the similar things should happen for resistance, or for example polarization. When I polarize an object or polarize a 3D mass by externally applied electric field, the polarization also is a tensorial quantity. What I mean is, if I apply electric field in along this particular direction and the body is polarized, there is a good chance that we will get a polarization along a direction which is perpendicular to the applied field direction as well. But please understand that none of these are specific to a origin, but moment of inertia tensor is. That is where the difference comes, because moment of inertia, this entire construction is valid for one particular origin. Moment I shift the origin, shift my origin, my total, the description of Ri's, the values of Ri's are changing. So that means in this integration, my in this integration my r square minus x square, r square minus y square, these quantities or x y quantities are also changing, right. So moment you shift your origin, you have to redefine your moment of inertia tensor. Thankfully, we can there are theorems which can be applied in order to shift the origin for a certain given that there is a specific symmetry in the object, we can always use that theorem in order to calculate the new moment of inertia tensor. We will come to that slowly, but for now let us move on from here. Problem is, when if you remember, we have this learned this definition of moment of inertia I. Let us say we have a rigid body, we want to calculate the moment of inertia around this particular axis which goes through the body. Okay. So, let us say if this is the position of ith particle, what we did was we calculated the distance di and we have defined moment of inertia as I sum over mi di square. That's what we have learned, and so in integral form it will give you d rho dv. Okay. D will be some function of x and y and z. So it's a distance, sorry, d square, right. So this is what we have learned, and now we are getting moment of inertia in terms of this complicated 3-dimensional matrix. How to correlate these two? Is there a way where how can I correlate this definition with that definition? So in one hand we have an equation that L is equal to I times omega, and in the other hand we have a definition I. Okay. This is a notation, both sided arrow, it is a notation of a tensor, right. So this is a tensor equation, that is how we define moment of inertia, and here this is a simple equation which is, there is no tensorial symbol, I is just a number, because we know that in terms of finally what we calculate is just a number, has a certain dimension, mass times distance square, but it is a number. How do you correlate these two? Okay. It turns out that a correlation of these two is also possible, but in order to do that, what we need to do is we need to calculate the kinetic energy of rotation, which is once again, if I consider for this fixed point, it will be mi vi square sum over all I. Okay, let us say this is the position vector of this. If the velocity of this particle is vi, so it will be mi vi square, and this will be half mi ri cross, sorry, omega cross r, omega cross ri square, right. So this is one way of this is a way of defining the total kinetic energy of the system, and this will help us in correlating this definition with the standard definition what we have learned during our school days. So we will take it up in the next class and start from here.